every Friday, all of SoMAS gets together for colloquium to talk about, listen to the hot topics of the day. So our speaker today is Kevin Reed. I was talking to you, we've known each other a long time now, right? I was talking to you about how approachable the faculty are. Kevin is one of those. I mean, as far as I'm concerned, he was a grad student just the other day. He, more or less, he is now professor of atmospheric science, but that's not all. Kevin has lots of titles. He's associate provost for climate and sustainability programming. I know you all appreciate good programming. He's the chief climate scientist at the New York Climate Exchange, an entity that we created that it aims to help New York City and other parts of the world transition to a new green economy. The interest in part of mitigating climate change. So this is one of the many reasons to come here. Kevin is a climate scientist who studies climate change and tropical cyclones and the damage they do and the impact of climate change on how much precipitation they drop. Let me not give his talk. He got his PhD at University of Michigan in atmospheric sciences. He also got a couple master's degrees, or a master's degree and a graduate certificate in science, technology, and public policy. Kevin is a star in the sort of areas that we want SoMAS to work on. How to connect our progress in understanding the fundamentals of how the Earth works, and then translate that into action that will do what we've discussed we want to do. Save the world and make the world a better place and minimize the impacts of humans. Kevin also was AAAS AGU Congressional Fellow in DC after his PhD, and so he is really in the middle of the realm of connecting science with action and public policy, doing good things for the planet. So I promised I wouldn't give his talk. Take it away.
Okay, well, hopefully the mic is working. It's on, so. And thank you for that introduction, Shep. I'm impressed with how much you memorized there. So I appreciate that. And I just want to, before I jump in to the presentation, wanted to just kind of set the stage a little bit, which is what I'm going to try to do in the next 45 minutes or so is talk a little bit about what climate change means for extreme weather. And try to connect that in some cases to what that might mean for extreme weather right here at Stony Brook on Long Island in the Northeast. But I'm actually going to do it by taking a big step backwards. And so I kind of took the liberty here and departing what I would typically do from a seminar, which is give some motivation and just dive right into the work that my research is doing. My research group, is working on. But I'm actually going to go back and we're going to start with the basics of what is climate change and why are we studying it? What are the tools that scientists use? And then I'll talk a little bit about some of the work that my group does. And so for the current students, this will be a repeat for some of the stuff you've already learned in your classes. For the faculty in the room, I think maybe this will just be a good reminder of some of the basics for everyone. And for the new students, or the potential new students, right, when you all agree to come, just try to give a sense of some of the topics that you'll learn about in the curriculum here. So let me first start though with, and Shep kind of already alluded to some of this in his introduction, with what really is my motivation for the scientific research that I do. And so, from my perspective, we're actually entering an era in which the numerical tools, so the models that have historically been used to assess long-term climate change, so these are climate models, are actually approaching the character, or let's say the ability that's conventionally used for short-term weather forecasting, meaning that historically for decades, climate models were one thing and weather models were another thing. And as time has gone on, they've actually started to be able to do some of the very similar things. And because of this, this actually gives us a chance to really investigate trends in extreme weather and look at and project the regional impacts of climate change. So it helps us better connect to the policy needs, the stakeholder needs, the community needs around better preparing for future climate. And that when we do this, that these type of approaches can have applications to other disciplines and communities. And I'll give an example or two of that towards the end of the presentation. But I said I was going to take a step back to start. So I'm going to take a big step back. So let's first think about where we are, right? So we're here on Earth. And I put the most important thing, of course, the images, everybody's seen these are some of the most famous images in the world. I start with this because it puts the date on here, right? So the first ever image that we kind of had in some regards of the entire disk of the Earth, right, from outer space was in 1972, which of course, right, to many of the prospective students, that seems like a long time ago, but the fact is for science and for a discipline of science, such as environmental science as a whole, that is actually not that long ago. Which means all that we've started to understand about the climate system and how it can impact weather, how it can impact ecosystems, is actually in the grand scheme of science relatively new. And it really started with these type of going to space and looking back at Earth and seeing how intricate and how complex it was, right? That if you want to try to understand the climate system, you have to understand everything that's going on in these images. And these images are just 50 plus years old. And what I focus on when I look back at that picture is this image, right? Which is this very, very thin layer here, which is the atmosphere itself. That's the layer that protects us from the harshness of space. It's also the layer in which all life, or majority of life, exists, and is the area in which most of the warming and climate change is happening, right? And it has a direct impact on, of course, our lives. And then, of course, where are we physically right now, right? We're on a small little part of that planet, right? So we're on an island that has a lot of unique characteristics. It has a range from a heavily populated area over by the city out to a more rural, although it's becoming less and less rural area out on the east side of Long Island. And we're surrounded by the Sound. We have the ocean to the south, and then we have all this complexity of our coastline and different land surface types just right here alone. So trying to understand, right, the global impact and model the climate system, but then to try to translate that to impacts that matter for humans on the time scales and spatial scales that matter for us is a really, really complex thing to try to do. And it's a really complex thing to try to do really in the last 50, 60 years of the science advancing. So, okay, so now I took a big step back. Now let's get moving a little bit and just start with what is climate change. I'm sure everybody in the room has some understanding of what climate change is, but let's go through some high level stuff really quick, which is first that despite the field of climate science being relatively new, the scientific foundation of our understanding of the Earth's climate is actually based on the fundamental principles of physics that drive all of science, right? They're based on the conservation of energy, conservation of momentum, and the conservation of mass. And so our understanding of what drives the climate system, and that the energy is coming from the sun and that's being distributed in different ways, is actually driven by our fundamental understanding of physics and radiative transfer and in chemistry and all of these things in biology. But in addition to the physical understanding from our fundamentals, that our foundation is also driven by a variety of diverse observations that have been collected, not over just the last 50 years, of course, with satellites, we've had a lot more coverage, but we've collected various forms of observations for the last couple hundred years, whether we're measuring temperature in locations, but even going back further with proxy data. And so our understanding of the fact that the climate is warming isn't just driven by these fundamentals, it's driven by a variety of data sources that, of course, have all different levels of uncertainty associated. And it's really driven, right? So I said I was taking a step back, right? So it's really driven by global energy budget, right? So I'm not going to go into detail here, but I always like to start with this because this is There's many iterations of this. It's been over time, we've used satellites to drive down the uncertainty in a lot of these fluxes, but ultimately our understanding of climate change is mostly driven by the fact that the amount of energy that comes into the Earth system from the sun in a balanced climate equals the amount of energy that goes out of the system, right? And so the way I like to think about that is if you have a bathtub and you fill it with some water, but then you start letting out some water, but you turn the faucet on so that the level of the water in the bathtub stays the same. If that's the case, you have an equilibrium climate. So if the energy coming in equals the energy out, right, we have a stable climate. If you turn the water up a little bit more, or if you change the amount of water that's going out through the drain, you will have a change in the level of that bathtub. And that's exactly that's the simplest way, in my opinion, to describe what climate change is. We are now changing the amount of energy that goes out to space. And we're changing it by changing the composition of our atmosphere and our land surface and a variety of other things, but mainly, first order the composition of our atmosphere, which means that the amount of energy leaving the system no longer equals the amount that's coming in, and actually more of it stays in, and that heat that stays in raises the level of the bathtub. It raises the temperature of the Earth system as a whole. And we can observe this from a variety of different ways, right? And so again, we don't just put these two plots next to each other and say, oh, they're both going up. So climate change is real. It's driven by carbon dioxide. It's driven by our understanding of what carbon dioxide molecules interact, right, with radiation from the sun or from the Earth itself, which is actually how it does it. But we do have observations going back to the late 1950s due to technological advances in measuring carbon dioxide in the atmosphere that it's actually increased by over 100 parts per million in the last kind of 70 years. And then if you go back even further, which we can do from proxy data, that it's increased even by more, over 150 parts per million. So it's increased by at least 50% of pre-industrial values, if not more, in the last 100+ years. And that this has corresponded with a pretty rapid increase in global surface temperature. So actually, this is an anomaly from the average, right? But you'll see that for most of our data collection around global temperatures, which of course there's some uncertainty in how you calculate, focus on the last 70 years since 1950, that the temperature has been steadily rising. And actually, if you look decade by decade, each decade since the 1970s has been warmer than the previous decade as a whole. And even in the last few years, you look at 2023 and 2024, these are the warmest years on record globally. And 2025, we're just a few months in, but it's likely to be up here in some area as well by the end of the year. And so the global average temperature in 2024 was about 1.5 degrees Celsius warmer than the pre-industrial area. So that's about 2.6 degrees Fahrenheit, which in the terms of climate is a pretty significant change to happen over just a 50, 60-year period. And most of that warming's happened in the last 50 years, and actually most of that warming has started to accelerate in the more recent decades. So why carbon dioxide? So I just want to start I emphasize at the beginning that this is a relatively new area of science, but I do want to kind of at least acknowledge that scientists have actually well understood the role that carbon dioxide and temperature play for well over 150 years. Actually, that we've understood that carbon dioxide is a greenhouse gas, and that it absorbs outgoing long wave radiation from the Earth and re-emits it in every direction, in which some comes back down and stays. But it's worth noting that it's not only carbon dioxide. So there's nitrous oxide, there's methane. All of these have been going up for the same reasons that carbon dioxide's been going up. And in addition, we can see that the reasons for those increases in carbon dioxide emissions are coming from things that we do as humans. So historically, going back to 1850, they've come a lot from land use, land surface changes, such as agriculture. In the 1900s, a lot of the increase in carbon dioxide started to come from coal power, burning of coal for electricity generation. Then over the second half of the 1900s, it started to come more and more from oil and natural gas. And you can see now in kind of the near term that the majority of it is still coming from oil, but as well as natural gas and coal. So even when we've converted in the last 20 years coal power plants to natural gas power plants, they're still emitting carbon dioxide into the atmosphere. In the United States, you can see the breakdown of this, that 25% of the carbon emissions actually comes from electric power generation. About another 25% comes from industrial operations and industry more generally, and about 25, a quarter, comes from transportation system. And so, right, so when we start thinking about solutions of how do we start reducing these amount of greenhouse gas emissions, we have to acknowledge that it impacts our daily lives, right? So many of you drove here, maybe some of you drove electric cars, but not everyone. Even if you drove an electric car, that electricity is maybe being generated from a power plant, which is coming from, coal, or in most of the Northeast, it's coming from natural gas. And we all rely on products, right? Our clothes, our makeup, or whatever it is, right, is coming from industry. And so there's kind of greenhouse gas emissions that are coming from all of these. Sorry, I should have mentioned that this is for 2022. So let's talk a little bit about some of the observed changes that we've seen in the system due to this increase in carbon dioxide, up to about 425 parts per million. One of the best tools I like to use for this is the National Climate Assessment. This is a report that's put out by the federal government in the United States supposed to be every 4 years. Sometimes it comes plus or minus a few years. And it's actually required by law, signed in by the first Bush in the early 1990s. And what you should notice is that if you look at the actual temperature change in the United States, and I have done the worst thing possible that we would learn in class not to do, which is I forgot the color bar. Okay, well, see, that's terrible. So let's start with the temperature, right? So the redder colors is the warmer temperature, and the yellower colors are less temperature changes. And what you can see is everywhere in the United States has experienced an increase in temperature over the historical record over the last 70 years, everywhere. Parts of the United States, this is oftentimes referred to as a warming hole in the Southeast. It hasn't warmed by as much or just a little bit. And there's reasons for this, and we're continually trying to understand. But we're up here, right? Here's Long Island. Actually, it's worth noting that the Northeast as a whole has warmed faster than the average in the United States, and faster than the global average. So when we say that the world is 1.5 degrees Celsius warmer than it was 150 years ago, the Northeast is actually warmer than that over that time period. So it's approaching 3 degrees Fahrenheit warmer in the Northeast, really over the last 70 years. And so when if you are from the Northeast, or from this, so those of you that live here and you hear somebody say, oh, the summers are warmer and the winters are warmer, the fact is that's true. It's a real thing. And it's showing up and it's manifesting in the change in our average temperature. And if you look at precipitation, you can see that there's this interesting dichotomy that kind of happens in the United States, where the eastern United States has become wetter over time and the western United States has become drier. But that doesn't mean that we aren't prone to droughts and the West isn't prone to a significant amount of rainfall. We actually see this all the time with atmospheric rivers in the western side of the United States, that these are the annual averages, and that if you start to look at extreme precipitation, it's actually increasing everywhere. And so here's one way to do that. Again, this is coming from the National Climate Assessment. Hey, this time I actually got the color bar on there. This shows you the change in the heaviest 1% of days. So if you look every year and you look at the days that have the most amount of rainfall, so the 3 most days with the most amount of rainfall, and you look at the magnitude of that rainfall and you compare it to what it would have been in the past, this is where the climate change signal is real, right? So the 3 rainiest days every year actually rain 60% more now than they did 70 years ago. Right, so and so these are your most impactful days already. These are the days like in Stony Brook just in August where we got 9 inches of rain in a 10-hour period. This is the fact that same event, right, would have maybe been a 6-inch rain event 70 years ago. And that has real ramifications for the infrastructure, because the infrastructure was built for 50 years ago. It wasn't built for now. And you can see that everywhere in the United States there's been an increase, except for maybe changes over. Of course, the Hawaiian Islands are doing something slightly different there. You can look at other measures. So the maximum daily precipitation over a 5-year time period, we've also seen increases in that. You look at the annual maximum precipitation daily it's increasing. So the extremes are certainly increasing, even if the averages are only increasing by a relatively modest amount. And here's just diving into this example right here for the Northeast rainfall, again, coming from the National Climate Assessment. You can see if you look at days, the number of days every year with over 2 inches of rain, those number of days have increased by 50%. You look at the, and this is in the Northeast as a whole. So it used to be in the Northeast, we'd have around 300 days that had over 2 inches of rain, and now we're approaching 500 days. And if you look at each as you increase to 3 inches, 4 inches, 5 inches, the scariest thing that's happening here is that percentage is just going up and up and up. And so there are actually 100% more. There's double the number of extreme precipitation days with over 5 inches of rain in the Northeast than there used to be in the 50s and 60s. And so to recap, right, the global average temperature on Earth has risen. It'll continue to rise because of the increased human addition of greenhouse gases to the atmosphere, as well as the changing of the land surface, which can also impact the greenhouse gases in the atmosphere. I haven't mentioned these, but I did put them in the slides, but I just want to mention that there's other aspects. I focused on weathers and extremes here, but there's other things that we've seen, right? The historical stable masses of ice on land will melt and will continue to melt, and we're already seeing this with mountain glaciers, and we're seeing this in parts of Greenland. Sea level will rise. Here's just a plot that I took from the IPCC. The sea level will continue to rise as we go forward in time. And what I'm going to now focus on when I start to think about the work that our group does is that the weather will continue to change. And so inherently, if the global average temperature, or if the average temperature on Long Island has increased by close to 3 degrees Fahrenheit over the last 70 years, by definition, that means that the weather has to have changed. You can't have a change in climate without your change in weather. And so what we try to do is try to explore what that means and try to quantify that in a way that can be useful for planning. But I want to start with, well, let's talk about extreme weather first. So we focused on the previous slides around just extreme precipitation, but I want to kind of just mention it and motivate that extreme weather can come in a variety of forms. Here still, despite some crazy precipitation we've seen just in Stony Brook, but in the region over the last kind of 10 years, the main event that still comes up when we talk about the impact of climate change in this area is Hurricane Sandy in 2012. And I know there's many people in this room. I didn't actually live here then. I actually lived in Washington, D.C. It was not nearly as bad there. But there are people in the room that, of course, were here during Sandy and have the experiences and the stories to talk about. But the reality is that when you have these extreme events, you can have impacts right at the coastline, damages right to homes and infrastructure. Turns out, jokingly, water flows to the lowest place that it can, which in a city is the subway system. And so if your protection of water out of the city fails at any point, all it needs is one failure point, the water will get into the system and go into the lowest part of the system, which is the subway system. And so we've seen this with Sandy, and still to this day, they're still building back the tunnels under the East River due to the salt water that flooded that was in there for days and weeks at a time. They're still modernizing the infrastructure of the subway from an event 13 years ago. It impacted, of course, cars. There's other effects that happens. You don't just get flooding. After flooding, it can ruin your electrical infrastructure and creates a lot of issues that can actually start to fires. And so that some of the biggest damages in neighborhoods were actually due to fires after the events. It's not just these type of events or hurricanes like Sandy. If you look at the NOAA puts out what they call $1 billion disasters, which is just a measurement of the number of events every year that cause at least $1 billion in damages. And so the first thing to note, it's kind of small here, but if you look, this is for 2024. In 2024, there was about, I think it was 27 events that caused $1 billion in damage in the United States. And they came from a variety of things. Of course, hurricanes are a big one. And actually hurricanes last year was around 5 storms that produced at least $1 billion in damages. Some years it's 1, some years it's more. but they're actually disproportionate in their the amount of damage. So oftentimes these events are causing tens of billions, in some cases over $100 billion of damage. But you also get events such as tornadoes, severe storms, and then you also can get events that are coming from snowstorms. You can get events that come from drought, wildfires, and heat waves. And if you look at a evolution of the number of billion-dollar disasters that have, first, quick note on the methodology is that this is inflation-adjusted numbers, right? So $1 billion here in this plot, $1 billion event in 1980 is the equivalent of what $1 billion is now. And you'll see that over the last 45 years, there has been a significant increase in the number of billion-dollar disasters, right? We went from around 4 on average in the 80s to now in the last 10 years, we're averaging about 3 times that, more than 3 times that. And of course, if you follow any of this in the news, there's discrepancy about how people use this plot. I want to acknowledge, I'm not using this plot to say that here is a clear signal of climate change, because there's other things that impact damages. This is what I would say is this is a clear showing of our society's continued increased risk that we put ourselves into these type of events. We're moving to areas like the coast that are more susceptible to extreme events. We're increasing our risk of exposure by that. We're moving to central locations. We're moving to cities. And so when a city experiences an event, the damages that can happen are more than it would have been 45 years ago or 100 years ago. So there's a human aspect of this, but also there is a clear signal in extreme weather. And the National Climate Assessment states, and I've been using the same, I probably used this statement actually in my job talk here when I came to Stony Brook, which is that changes in extreme weather events are the primary way in which people will experience human-induced climate change. And that we're already seeing these increases in the number and the strength of the severity of these events. And I think that this plot does partially show you that. So while we're making ourselves more susceptible to extremes and more vulnerable, the climate has significantly changed over the last 45 years. So we are also changing. The extreme weather events are also changing. So I want to spend a few minutes. I said I was kind of giving an overview, so I want to spend a few minutes just talking about the different types of tools that scientists use to explore climate change and its impact on extreme weather. And then I'm going to finish the last little bit with some of the work that our group here at Stony Brook has been doing to sort of quantify some of these impacts in ways that are more actionable. So first, the primary tool that scientists use to project and not just project, but also understand historical past climate change is through the use of computer models. Computer models of climate are imperfect tools, right? So all models are bad. Some models can be useful. And they're mathematical models that are simplified versions of the real climate. Going back to those satellite images that I showed at the very beginning, right? The level of detail and the range of processes and feedbacks that happen in the climate system is immense. Because of this complexity, what climate models try to do is they try to capture as many of those important feedbacks that they can numerically, either through the laws of physics, the understanding of fluid flow on a rotating sphere, which we understand really well, and we can solve for using equations of motion, the Navier-Stokes equations, or through estimations, through parameterizations of what these type of processes are, the important feedbacks that we know exist through lab experiments or through field campaigns or other ways in which we've collected data around specific processes in the atmosphere, as well as the ocean, in land surface and ecosystems. And so ideally, we want to capture all of those in feedback, right? Clouds, the impact of the ocean, the impact on overturning circulations, the impact of photogenic, all these different types of things. And we do the best we can, but they're imperfect. And I'm coming back to this just because we can't capture everything. And then also the struggle that we do is in order to do this numerically, like any numerical model, you have to come up with it. You have to grid yours into boxes, right, that are stacked on top of each other to represent the atmosphere. They're stacked on top of each other and it goes into the ocean. There's different types. The dimensionality shows up differently in land with different soil layers, but also A lot of these climate models have over 60 different plant types now that they account for. And so it's a really complex system, but this is what we use to not only map historical climate, but to look at the future. And so one of the ways we use models is to actually understand the observed climate change that we've been talking about. So we can understand what is actually responsible for the increase of a degree and a half Celsius that we've seen over the last 100+ years, and most of that again in the last 50 years by doing model experiments in which we can run the last 170 years of the climate system with only natural variability. So only changing solar input based upon solar cycles and the output from the sun, and including volcanoes, which of course can impact the composition of the atmosphere. And if you do that, you get this blue line. And the black line is the observed climate change. The black line is observations. And so what we can see is that if you only include the natural variability in the system and you don't change greenhouse gas in the atmosphere, emissions in the atmosphere, you cannot replicate the warming that's been observed. And that actually it's through the inclusion of different types of human and sometimes not just greenhouse gas emissions, but changes in land surface type and things like that. That's the only way you can actually capture the warming that we've seen over the last 150 years. And so models are actual tools to not project future climate. They're also tools to help us understand what drives the climate we live in now. And you can actually do things where you can break down the warming that we've observed by all the different contributions from human emissions, from carbon dioxide, methane, nitrous oxide, but there's other different gases. You can look at some emissions, such as sulfur dioxide, right, impacts aerosol growth in the atmosphere, which can lead to increasing the reflectivity of the Earth's atmosphere, which has actually decreased some of the warming. So actually, without these emissions, the world would have warmed by more, and we're actually seeing this now as these are also harmful for human health. And so we've actually seen a decrease in these emissions, which is actually increasing the warming signal so on. But we also use these models to project the future, and they're meant to build out what the future could look like based upon various socioeconomic assumptions. And so they make assumptions around land use change in the future. They make assumptions about population growth, right? Because the amount of people we have on the earth dictates how much energy we need, right, for keeping the lights on and for products and all these different types of things. And then they often make assumptions about energy transitions, right? Whether we're going to continue to be a more fossil fuel heavily industries, or whether they're going to migrate more to renewables or less energy consumption. And so there's a range, but what I want to harp on two things from this is, first is that the future will not look like any of these. These are projections. They're meant to be almost thought experiments, right? Of what happens if we live in a world in which we continue to increase greenhouse gas emissions at the rate we're doing? What happens if we live in a world in which we rapidly transition to renewable energy? They're meant to be ways to help inform international mitigation policy around greenhouse gases and climate change. So that's one thing, and you can notice that these are just two of them. One is RCP 8.5, which is a pretty kind of business as usual. It might be an extreme case based upon some of the improvements already we've seen in the last decade in emissions. And this, the blue one is the RCP 2.6. This is a world in which we actually meet the Paris Agreement and keep it to less than 1.5 degrees Celsius. So you can tell this is a little bit dated because we're already at 1.5 degrees Celsius. But this is from the previous IPCC. But the first thing you'll notice is that the scenarios show you that by the end of the century, you can have pretty large differences in global average temperature between something like 1.5 or over 4 degrees Celsius, based upon the decisions we make in the coming decade around what we use for electricity generation, greenhouse gas emissions. The most challenging thing about all of this is that you don't see a difference in the things that you do now in the global average climate system until about 2050, if we're lucky. Meaning we won't reap the benefits, right, of mitigation policy now. And there's many of us in the room that might not ever reap those direct benefits from a climate standpoint, because the difference in the impact doesn't really show up into the second half of the century. However, there are additional impacts that come from these things, like the improvement in our air quality if we reduce greenhouse gas emissions, for example. So there are direct impacts that we can have from mitigation. And then these models are also used, they include fully coupled ocean systems. They're used to measure or to project future sea level rise, which actually has a lot of uncertainty. They're also used to look at changes in the cryosphere. And so one metric is when will what is the sea ice extent in the Arctic? And one of the interesting things is that these models have started to show us that originally we thought maybe by the 2050s we'll actually have a time in which in the summer the Arctic, in the late summer the Arctic will be ice free. And what we have actually learned is that these models are actually maybe slightly off, and it'd probably be sooner than that. And so these have real implications for understanding actually geopolitics of transportation around the world as well. And then I'm not going to go through these really quick, but the IPCC puts out plots like this, which shows you, okay, what is it, 1.5, 2 degree? This is the world we're kind of living in now. What does a 2 and a 4 degree warmer world look like from a temperature standpoint? You can see that one of the things to note is that the land is warming much quicker than the oceans, at least at the surface, which has a direct impact on, that means that the land average temperature in a 4 degree warmer world is actually larger than 4 degrees, right? So the impacts are even larger where people live. Most people live on land. And then of course, when you look at rainfall, which is shown down here, you can see that this is where it gets a little bit complicated. Some areas are getting more rainfall, some places are getting less, and there's a lot of uncertainty around this. The National Climate Assessment does the same thing for the United States and North America as a whole. They look at changes in temperature and changes in extreme weather. I mean, the main story is consistent: increase in temperature and an increase in rainfall, and especially the extreme precipitation. And this is just a quick note, which is actually that the New York State puts out its own climate assessment, which actually does the very same thing, but almost at the region level in New York, which tells the same story. That in the next 30 years, Long Island will experience some of the largest increases in rainfall in the state, and that rainfall will continue to increase in some cases up to over 11 more from the recent climate percent in the future. And this is annual precipitation. Most of that precipitation change is coming in extreme events. Okay, so that's the high level overview. I'm gonna spend the last kind of 10 minutes just walking through some examples of the work that our group does here at Stony Brook that tries to look at some of these impacts in ways that can be helpful for understanding regional change, but also what that means for resilience and adaptation strategies. So our group focuses on using climate models. We make use of the public climate model that was built at the National Center for Atmospheric Research. It's the community or system model. We're often using the atmospheric component. So we're running with different resolutions, generally around 100 kilometers. This is what's conventional used for those IPCC results. All the results that we just showed typically use really coarse versions, 100 kilometers by 100 kilometers. So that means that you maybe have about, I don't know, 5 grid boxes on Long Island as a whole, just to put it in perspective. And then what we also, I'll show some results of where we go to what we call high climate resolution, which is 25 kilometers, which is actually not that far off from what operational weather models use for their ensemble forecasts in terms of resolution. So that if you're looking at your favorite weather app on your phone, the information that's going in to tell you what the weather is going to be like tomorrow or next week is actually coming from models that have somewhat similar resolutions for their ensemble forecasts. So here's just a quick high-level example that I've been showing for well over 10 years now, which is if you take a conventional climate model and you run it for 25 years, it's 1980 to 2005, and you run it at its typical 100-kilometer resolution, and you want to look for hurricanes, tropical cyclones in them. This is the number of storms you get in a 26-year simulation, right? So you can see there's a very few of them. They have interesting north-south tracks, and there's maybe about 1 to 2 a year. If the only thing you do is change the resolution of the model and go up to 25 kilometers, which is a big increase, a significant 30x increase in the computational cost of the model. So this isn't trivial to do. You can see that now this is the number of tropical cyclones you get. So not only do you get a lot more in the basins you'd expect, you're actually getting larger intensities representing what we see in reality. And if you just can kind of compare between the high resolution climate model and observations, you'll see that it's doing a lot of things right. But remember, models are imperfect. You'll see that it's getting some storms in the Central Pacific where it shouldn't be. It's maybe not capturing the full intensity range, but it does provide some credibility that you can start to use these models to say, okay, let's go back to those projections that we were just talking about of the future of a world in which we continue greenhouse gas emissions versus more worlds in which we start to reduce greenhouse gas emissions. Can we look at how tropical cyclones would change there? And so this is a plot that shows you the observations, and the blue is the historical simulations I just showed. And the first thing to notice is that the models are imperfect. They have a bias. They have less storms than we see in reality. But if you focus on the red line, this is the kind of the future world that would be about 4 degrees warmer at the end of the century. And what we see is that there's actually a statistically significant decrease in the number of tropical cyclones. That you heard me right, a decrease. In a future world, there will be less. There's a possibility that there'll be less hurricanes globally. But if you look at the end here, which is where you see the strongest storms, again, the model struggles at representing them, but it's able to get around 5 per year, as opposed to the kind of 12-ish that are observed. But here you see that actually the number is increasing. So we're seeing a decrease in the number of overall storms, but we are seeing a significant increase in the number of the major storms, the ones that reach category 3, 4, and 5. These are the Hurricane Irmas, the Ians, the Harveys of the world. So these are the ones that actually have the biggest impacts, and these are these all models and all theory actually agrees that we're going to see an increase in intensity. So some of the things that our group does, so knowing this is an important scientific thing to know, and there's a lot of ways to explore it. How you translate that to a community on Long Island that's trying to think about how they prepare for the fact that they might be less storms, but when they happen, they might be stronger. It's definitely never going to be through a plot like this, right? This is a global plot. It's important for science, but it's not translatable to action or to resilience. And so some of the work that we've done as part of a Department of Energy project called Hyperfacets is that we've actually worked with water resource managers across the United States to actually develop different types of metrics that we can use to run through those simulations in ways that would be more useful to them. So when we've worked with water resource managers, of course, the first thing we learn from a water resource manager is they really care about precipitation, rainfall, obviously. And so what we worked with them to do is to build a metric that would quantify the amount of rainfall that's associated with hurricanes, and then start to understand how that rainfall might change in the future, because that's something they can start to plan for potentially for infrastructure design, road design, and things like that. And so we developed a metric that can extract precipitation only from tropical cyclones, and it's actually dynamic. So as the storm changes in size, the way in which we extract the precipitation, a big storm will extract precipitation at a wider amount than a small storm. And so we actually captured for the dynamic changing of stone size. And so here's just a quick example of what we've been able to do. So now we're honing in just on the eastern United States. And if you look at this, the first thing you'll notice, this is a historical climate. These are future climates. We don't have to worry about which one. Just note that first thing you notice, this is track density. This is a number of hours per year that grid point experiences a hurricane. And so what you'll see is that if in the future, there's a decrease. That's consistent with that plot we were showing earlier. There's a global decrease in storms, and we also see regionally a decrease in the amount of hours of impact of storms. Now we look at the rainfall that comes from those storms using that metric we developed with the stakeholders, and what we can see is, expect most of the rainfall that comes from hurricanes occurs right along the coast. A lot of it's in Florida. Here, okay, there's less storms in the future, less hours of storms, which means there's actually less rainfall from hurricanes in the future. So that's maybe an important thing to know. But what the stakeholders told us they really wanted to know was what's the amount of rainfall per storm, or per hour of impact. So if you take this column and you divide it by the hours of impact, you get the amount of precipitation per hour of impact of storms. And this is the result, which shows that while there might be less storms in the future, particularly in some areas, when they do make landfall, the amount of rainfall that falls per hour of impact is significantly increasing, on the order of, in some cases, 50% by the end of the century. And so this got us thinking, okay, we're learning that storms might be decreasing, but when they do make landfall, the precipitation is increasing. So then we said, hey, the world is warmed by over 1 degree Celsius, almost 1.5 degrees now. That means that precipitation maybe has already changed in these storms. And so what we did is we developed a way to look at this to kind of translate that climate impact of more rain per hour of impact into something that's even more actionable than just saying that from a climatological sense. So what we did is we took our climate model and we turned it into a weather model because it operates at similar resolutions that a weather model is. So we run our model, and instead of running it for 25 years, we actually just initialize it in the advance of a storm making landfall, and we run it for 7 days, just like an operational forecast. And so we've done this for actual storms. So here's Hurricane Florence. We initialized the model on September 11th at 0Z, Hurricane Florence from 2018. And we can run an actual forecast. So here's 100 ensemble members initialized at that time, showing where the track of Florence goes. So it actually, and the black line is the actual track of Florence. And so what we can see is that the model actually can nail the point of landfall quite well. Every operational model 3 days before landfall struggles with track later in the simulation time. And so we didn't capture this turn of the storm, except a couple ensemble members did. But we were able to capture the location of landfall. And then the nice thing we could do, since we're running a climate model, we actually have we're running in weather mode, but we have the climate change signal that I was just showing you from the previous work, right? So we can go really quick. If we go all the way back here, we have these runs where we know what the world would have been like without climate change. We can calculate this signal, this 3D fingerprint of the warming to date. We can remove that from our initial conditions into our weather version of the model, and we rerun it as a counterfactual. So what would Hurricane Florence have looked like without the large-scale thermodynamic warming that we've observed over the last 150 years? And again, you'll notice the track is pretty well. It matches pretty well the actual as well as the observed for a big chunk. The landfall locations are the same, and that means that because we've only changed the large-scale thermodynamic impact, the storm's track is somewhat similar. So we can compare apples to apples, the counterfactual and the actual then to see what was the climate impact on rainfall. And so here's just an example of how we did this with Hurricane Florence. Here's the observed rainfall. Hurricane Florence dumped over 30 inches of rain in parts of North Carolina in just a 2-day period, right? So 30 inches of rain, right? That's more rain than a lot of places get in a year, and they had it in 2 days. So this produced catastrophic impacts in this region. Here's our actual forecast. First thing to note, this is a 100-member ensemble, so it's much smoother than the observed, which is just one realization. But the model is still able to capture an area near landfall of over 30 inches of rain. It's in a slightly different location because it was initialized 3 days in advance, and there's always uncertainty. But if you compare it to the counterfactual, the forecast in which climate change was removed from the initial condition, you see that there's a pretty substantial decrease in the amount of rainfall. We can actually do the fancy statistics and calculate the significance, and we can actually state that the rainfall, the observed rainfall in Hurricane Florence was actually increased by 5% due to observed warming to date. 5% doesn't seem like much. I'd take a 5% raise today if the dean wanted to give me one. Because because that is you think 5% doesn't seem like a lot, but it's a significant amount, especially when you have 33 inches of rain. This is the difference between your levee failing or your basement flooding or not. And so the impacts of a 5% change in rainfall on damages is much larger than 5%. So just to finish up, we've done the same. We've now started to apply this in a way that's even more actionable. We can do this objectively. We've given an example through the 2020 hurricane season. It was the most active hurricane season on record. We just ran these forecasts every 3 days. We created thousands of simulations through the season, and we can compare the actual to counterfactuals. We can do fancy things like this, but through the entire hurricane season, we saw that actually there was an increase of 10% attributed to climate change in the 2020 hurricane season, denoted, extreme rainfall rates due to climate change. If you focus only on storms when they're hurricane strength, this percentage is actually larger. And so it suggests that first, the Florence work wasn't just one-off, but that when you do this operationally, then all of these other storms that had impact elsewhere, they now are armed with this information that the rain has changed, and they can start to plan for that when they're building back after a disaster like these storms. And now we've even started to do this in real time. So just a quick example is for Hurricane Ian in 2022. The night before, since these are forecasts, the night before Ian made landfall, we were already able to do the analysis, and we already at the time we had put out on Twitter that that we anticipated that the rainfall rates would increase by at least 10%. And when we did the more formal analysis, it actually came out to 18%. And the final thing to mention is that we're also doing this where we're looking not only at past climate change, we're also looking at storms like Irma, and we're saying how will the rainfall change in a 2, 3, 4 degree warmer world, so that when you're making design decisions, a lot of our water resource managers are either based here in Tampa or over here in the Miami area, and they actually can use this information to go through their design scenarios for storms that they use to stress their water systems. And I want to just, I can't give a full talk without at least mentioning reduced complexity models really quick, because I focused a lot on the applications. But a lot of our understanding of how and why rainfall is changing as the surface temperature warms in these climate models, as well as then observed, is that we've actually been using these models to understand the basics of what controls the number of tropical cyclones. We do crazy things where we get rid of all the continents on the planet. We run the same climate model. We have the same constant SST everywhere, and we just increase it. Interesting thing, really quick. When you get rid of continents and you have the same sea surface temperature everywhere on Earth, so you can think about it as an exoplanet that's just thermally heated from its core, you get tropical cyclones everywhere. It's actually the dominant phenomena that shows up. They form at almost the same spot that they form in the real world, and they move towards the poles. They just so happen to not have baroclinicity. There's no temperature gradient, so they don't die. They actually just go to the poles and merge with each other. But we can use these idealized models to actually look at, as the temperature warms, we can see we get an increase in rainfall. We get changes in the number of genesis. The genesis goes down in these idealized models as you increase the surface temperature. That's exactly what we saw in the comprehensive model. So we actually can use these models to understand what's controlling it. It's the change in the seeds that are leading to it. We can look at changes in intensity and the size, and we're able to actually calculate, when we see these percentage changes, we can actually calculate what percentage comes from the thermodynamic effect of the sea surface and temperature, so more moisture, versus what's coming from the fact that the storms are stronger. So we actually are rooting those things that we're doing for them on the more application side with an actual physical understanding of what's actually happening in the cyclones. So I went a little bit long, but I'll finish with just saying that in summary, I showed a little bit that extremes are changing. I showed some examples of the way our group is trying to quantify and understand that, but that's just one. I focused on hurricanes. There's a lot of different ways in which the extremes are changing. We're having warmer and fewer cold days and nights, hotter and more frequent hot days and nights, more frequent heat waves, more frequent droughts, changes in intense precipitation, and hurricanes. These are the ones that I showed. So with that, I have hopefully some time for questions, but I want to first thank that most of the work that we do is done by the members of the research group, who some are in the room here. And so thank you for your attention.
So every Friday, so there's a class that is associated with this seminar, which is all the first semester or first year graduate students. And so we offer the first question to the current graduate students. And so the two that have signed up for today are Megan and Sophia.
Hi, thank you for that talk. That was awesome. One question I wanted to speak on a little bit is one of the biggest criticisms I've heard of the idea that there will be increasing storms, extreme events, especially hurricanes, is that there's just not necessarily an increase now, but a lack of reporting and documentation in historical events. What would you say to convince those people that the models that we do have now, the means measuring like sediment cores, are doing an accurate job of recreating those historical times?
Are you referring specifically to hurricanes or tropical cyclones? Yeah. Yeah. Okay, that's a good question. So, of course, we are always going to be somewhat limited by the fact that most of our data around tropical cyclones has come since the satellite era, right? So the 1960s, and so we can verify or evaluate our models against how well we can represent the number of storms in the regions and distribution based upon that kind of 50-ish year period sense. And that provides some credibility. There is also work that has tried to recreate the amount of tropical cyclones across all the basins going back to at least 1900, and some is pushed back to about 1870 now, using a variety of things, using newspapers, ship logs, because at the time ships would, they didn't have forecasts then, right? So of course they could see ways in which the weather was changing, but oftentimes they would note that the weather was changing or they changed their course, and we can actually relate that back to that there must have been a hurricane out in the middle of the basin which didn't make landfall, so it wouldn't have shown up in the newspapers. And so they're actually able to kind of build back some of these more historical things in doing it this way. So we've actually, I think, have a reasonable representation, even going back 150 years that we can use to validate the models. Of course, the uncertainty is larger than that. The other thing that's worth noting is that there is a subdiscipline of tropical cyclone work that has the coolest, I think, subdiscipline name ever, which is paleotempestology, in which they actually can go back and look at sediment cores, as you mentioned, near the coastlines or in ponds and things like that. And there's actually been evidence to show that where we live here, right on Long Island, or where we're based at least, and some of you will live here if you don't already, is that actually there have been times in the past where there was actually way more cyclone activity than we see now. And that actually provides additional evidence to what we've been saying, what the models are saying, that it was cooler in the past and there was actually more storms. And so, you have to piece together the different lines of thought. And so it's not just the models, right? We use a variety of other things, whether it be ship's logs, whether it be sediment cores, to try to piece that together. Your question is still really important, because it's unclear actually at the moment of if the number of storms will actually decrease, because there's a pretty hot tested debate in our subdiscipline and meetings where some people say that they've already decreased and some are saying that they haven't, depending on how what you use. Whether or not they actually change in the future, the main takeaway isn't the number of storms, it's the impact when you have a storm. And so what the models are consistent with the observations, which is consistent with even some of our analysis through paleoclimate stuff, is that the storms are becoming stronger. The exceedance ratio of certain thresholds of intensity have increased in observations, and the models are showing the same thing, and our simple storylines analysis are showing the same thing. So that's starting to provide evidence of whether or not the number is changing. The strongest storms are certainly getting stronger.
So I guess I was wondering, like, is there any evidence or ways that we can convince people it's still important to continue to
Yeah.
Actually,
Yeah. Well, so yes. So great question. The first is to mention that the benefits of mitigating our greenhouse gases, right? It's motivated mostly by the fact that we know that if we continue to increase greenhouse gases, the Earth will continue to warm. And so in order to meet things like the Paris Agreement, which is to keep the Earth at 2 degrees Celsius warmer or less, the only way that we have to do that, that I think is justified, is to mitigate greenhouse gas emissions. So that's why we talk about that. Of course, geoengineering is another way that people have proposed, but I think there's a lot of other ethical issues. But at the same time, there's other benefits that come from mitigating greenhouse gas emissions. The first is that we have, just as a society, just come reliant on the fact that we're okay with pretty crappy air quality everywhere around cities, because it's actually a byproduct of the process in which we create our electricity. And that actually, if you were to start to turn off all natural gas and coal power plants right now in the Northeast, that within a week, our air quality would be better. And so the reality is that there's a public health benefit from the improvement of our air quality. But then, the other aspect of the innovation that comes from changing the forms of energy, the better grid resilience we could get by building a grid that actually can be more resilient to different types of extreme events, where you have a more distributed energy source. That there's all these other benefits that come from decarbonizing that isn't just related to the fact that in 2050, maybe we'll start to see a difference in what the temperatures in our global average would be. So I hope that answers the question.
Do have time. On the general on.
But you and then Brooke, yeah.
So, I know that this is kind of like a question of scales, but I think it's interesting that like with the increased rainfall. Or I'm curious if in your model, if you're able to see any changes in like the microphysical dynamics of the storms that cause that increased rainfall, or is it just with higher temperatures, there's more water vapor in the atmosphere?
Yeah, that's a really good question. The answer is sort of yes and no. So we are able to tease out that the main dominant factor that we've calculated, around 70% of the precipitation change that we've seen on an average in the storms comes from from what you mentioned at the end, which is just if there's more water vapor in the atmosphere, then there's more water vapor to condense and produce rain. Another about 20% actually comes from the fact that when there's more water vapor in the atmosphere to condense, that the heat engine that drives a storm actually becomes more efficient. And so you actually get stronger winds, which leads to more convergence, which leads to more uplift. And so you actually, about 20% comes of that rainfall just comes from the fact that the circulation has strengthened, because the winds are stronger. And then to your other point, our models are probably maybe not as good so far at getting to the point, okay, what are some of the microphysics changes that are occurring, and what's the role there? I would say they're probably somewhat captured in the broader thermodynamic change, but there are folks that have started to, and some people even here that look at the role of different microphysics in the simulation of cyclones and trying to understand, convective towers and what role they play in diabatic heating and genesis and things like that. And so there are tools that are out there that use it. We have climate models are a little bit are kind of constrained to the physics parameterizations they use, because you actually have to worry about that global energy balance, and just changing a microphysics scheme can have a huge impact on your balance of the model. Yep. Right.
So my parents, they live in the Midwest.
Yeah.
And I was interested in your plot there of surface temperatures and how there was, a lack of increased temperature in this south east area. And I just wondered if you had any, went over it, and I understand why, but do you have any idea why there's no increasing temperatures in this area?
That's a good question. And the short answer is I really don't. And so I shouldn't try to answer, but I will provide. But as an academic, I'll pontificate for a minute. Which is one of the thoughts is that there are changes in the seasons. And so if you look in the summer season, that it still is warming, and it's during the winter season where there hasn't been as much warming. And so the thought is that maybe there is some slight adjustments in wintertime weather, or a slight shift in the jet stream, which can lead to just a slightly different regional circulation that's mitigating it. So that's one of the things that's proposed. But actually, there are people that are proposing right now to do research to try to understand what it is. And interesting, as a quick side note, is that the Department of Energy actually has one of its ARM sites for atmospheric and radiation measurements that's actually now based in Alabama, right about here, specifically to try to explore some of the cloud processes that are happening, especially around the forests, and to try to partially help to create a data set to try to understand some of these things. So it's an actual active area of research too.
If there are no more questions, then I think everybody.